My name is Ahmed Mijul Nawaz. My student ID is 0377209. Hello, everyone, and welcome to today's presentation on data mining presented by Group 6. In this presentation, we will explore how machine learning can help address the growing crisis of accidental drug related deaths. As recent studies indicate, accidental drug related deaths are on the rise and have become a major public health concern. This crisis demands urgent, creative, data driven solutions. Traditional statistical methods often fall short when dealing with the complex, multifaceted nature of this data. Hence, our approach involves a multifaceted strategy combining classification, clustering, anomaly detection, and regression techniques. Let's now look at the first major component of our project. The problem statement here is clear. Accidental drug related deaths are escalating due to fatal overdoses from multiple substances. To effectively prevent these deaths, it is critical to understand the underlying patterns and the predictive factors at play. However, traditional methods struggle with the complexity of the data. This is where machine learning steps in, capable of processing large scale datasets to uncover hidden insights. Our objective is twofold. First, we leverage classification models such as random forest, decision tree, and k nearest neighbors to predict the circumstances surrounding these deaths. Secondly, we apply clustering techniques using k-means, db-scan, and Gaussian mixture models to group similar cases and reveal underlying patterns. Additionally, we implement anomaly detection methods like isolation forest, local outlier factor, and autoencoders to identify irregular patterns, and we employ regression techniques, including SVM, linear regression, lasso, and ridge, to explore associations between key variables like age and sex. Ultimately, our findings aim to provide actionable insights for healthcare professionals. Now that we've set the stage with our problem context and objectives, let's dive into the critical data pre-processing and cleaning steps that underpin our machine learning pipeline. Ensuring that our data is clean and consistent is essential for reliable and unbiased model performance. The first step is data pre-processing and cleaning. Raw data can be messy. It often contains inconsistencies, missing values, and redundant information, all of which can hinder model performance. In our dataset, one key challenge was missing values in numerical features, particularly the age column. If these missing values are not handled correctly, they could lead to errors or biases during training. To address this, we employed the simple imputer from the sklearn impute module, choosing a mean imputation strategy. This method replaces missing age values with the average value, ensuring that our data distribution remains intact and that we retain as much useful information as possible. Next, let's discuss handling missing values in categorical data. In our dataset, the target variable is manner of death, which is crucial for our classification models, since unknown target labels would undermine the training process. We opted to remove any records that had missing entries in this key field rather than attempting to impute them. This decision helps maintain the integrity of our training data and prevents any misleading information from impacting our model predictions. Now let's move on to encoding categorical data. Machine learning models require numerical input, but our dataset includes categorical features like sex. To convert these into a format suitable for our algorithms, we use the label encoder from the sklearn pre-processing module. This process converts categorical values into numbers. Male becomes 0 and female becomes 1. This ensures that all features are compatible with our models and can be processed effectively. After encoding, the next step is feature selection. Selecting the right features is crucial because it reduces noise and unnecessary complexity, which in turn improves both model interpretation and performance. In our study, we focused on the predictors age and sex, as these have shown significant connections with the manner of death during our exploratory data analysis. By concentrating on these key features, we not only improve our model's operational efficiency, but also reduce the risk of overfitting, ensuring more robust and generalizable results. The following step is data standardization. Many machine learning models, especially those relying on distance metrics like support vector machines or SVM, KNN, K nearest neighbors, and various clustering algorithms perform best when the features are standardized. Standardization transforms the data so that each feature has a mean of 0 and a standard deviation of 1. In our project, we applied the standard scaler from sklearn preprocessing to the age and sex features. This step is critical as it ensures that no single feature unduly influences the model simply because of its scale, leading to more balanced and accurate learning outcomes. Finally, before we move on to the model training, it's important to split our dataset into training and testing sets. We used the train test split function from sklearn model selection to divide the data into 80% for training and 20% for testing. This ensures that our model is evaluated on unseen data, providing a realistic measure of its performance. Additionally, the function preserves the original class distribution, and by setting a constant random state, we guarantee that our data partitioning is reproducible across different runs.
Hi, my name is Chongbit Shan. My student ID is 0340844. Today, I will be presenting our analysis on the evaluation and validation of machine learning models, focusing on classification, clustering, anomaly detection, and regression. Evaluating a machine learning model is an essential step in ensuring its reliability and accuracy. Without proper evaluation, a model may perform well on training data but fail to generalize to new data. We will explore various evaluation metrics and validation techniques that help assess model performance and ensure it meets the intended objective. In our study, we evaluated three classification models, which are random forest, decision tree, and KNN. These models were assessed using accuracy, precision, recall, and the F1 score. Each metric provides a different perspective on model performance, which is crucial when dealing with imbalanced datasets. Random forest is an ensemble learning technique that combines multiple decision trees to improve accuracy and reduce overfitting. Our implementation consisted a random state of 42 for reproducibility. By aggregating multiple trees, the model enhanced stability and generalization. Decision tree classifiers split data into hierarchical structures based on feature properties. They are highly interpretable but prone to overfitting when deep trees memorize the training data. To address this issue, pruning tasks and setting depth constraints can be employed to ensure better generalization. KNN is a simple yet powerful non-parametric algorithm that classifies data points based on the majority class of their nearest neighbors. It performs well for complex decision boundaries, but can be computationally expensive for large datasets. The choice of the parameter k greatly affects the model's performance, balancing bias and variance. All three models achieve an accuracy of 99.62% and precision of 99.25%, performing perfectly on the dominant accident class. However, they struggle with minority classes. Despite similar performance, random forest is the best choice. It is more robust against overfitting, generalize well to new data, and provides insights into feature importance, making it superior model for classification tasks. For clustering tasks, we applied k-means, DPS-CAN, and Gaussian mixture model, which is GMM. This model will evaluate using the Silholtz score, Davis-Bottin score, Kalinske score, and Ajets-Rand index score, which help measure the quality of clustering separation and compactness. DPSCN has the highest Silton score, indicating good clustering separation, but it performed the worst in Davis-Bottin scoring. K-means, on the other hand, had the best Davis-Bottin score and the highest Kalinske score, suggesting well-defined and compact clusters, given its strong overall performance. K-mean is the best clustering algorithm for this dataset. We implemented isolation forest and local outlier factor for anomaly detection. Isolation forest detected 589 anomalies, while LOF identified only 154. Since isolation forest is designed to efficiently isolate anomalies by randomly selecting features and splitting the dataset, it captures a broader range of outliers, making it the most effective choice for anomaly detection in this dataset. We compare linear regression, lasso regression, ridge regression, and SPM using mean squared error, which is MSE, as the evaluation metric. Lasso regression achieved the lowest MSE at 0.193133. Its key advantage is L1 regularization, which helps with feature selection by reducing the coefficients of less relevant features to 0. This improves model interpretability and prevents overfitting, making lasso regression the best choice for this dataset.
Hi, my name is Lin Kenny and my student ID is 0352896, and today I'll talk about data visualizations. Briefly explain this ROC curve, which evaluates our multi-class classification models. The x-axis represents the false positive rate and the y-axis shows the true positive rate. Each color line corresponds to a class, and the black dashed line represents random guessings. The AUC values are 0.96 for classes 0 and 1, and 0.97 for class 2. Since all values are close to 1, our model performs very well in distinguishing between classes. In short, the RC analysis confirms our model's strong classification abilities. This plot shows K-N classification with K equal to 5 for 4 categories. Each color region represents a decision boundary, and the dots are actual data points. Can assign new points based on their 5 neural neighbors, while boundaries are well defined, so overlap exists. A higher K-smooth boundary reduces noise by losing details. KNN is simple yet effective but depends on a well-defined dataset for optimizing performance. This plot showing binary classification using random forest with purple and yellow region as decision boundary. Those represent actual data points. Random forest build multiple data trees, classifying new points by majority vote. Its compressed boundary captures patterns but may risk overfitting. These powerful flexibility models balance accuracy and robustness for real-world application. For clustering, K-mean is an unsupervised algorithm that groups data in 3 clusters, which is blue, purple, and orange. It assigns points to centroids and updates until stable. Though effective, it assumes circular equal-sized clusters. K-mean is used in customer segmentation, anomaly detection, and image compression. So for DPSCAN is a distinct-based clustering algorithm that detects clusters for different shape and size while identifying noise 2-point cluster minus 1. It defines core borders and noise points based on a neighborhood, radius, and minimum point. Useful for anomaly detection and spatial data analysis. So for Gaussian mixture models, which is GNN, assume data comes from multiple Gaussian distribution, allowing flexible elliptical cluster. Unlike K-means, GNN handles overlapping and non-circular shape. The plot showed three clusters with distinct colors and boundaries, making GNN ideal for complex patterns. So for anomaly detection, this visualization shows the isolation forest decision boundary for anomaly detection. Inlier, which is yellow, are normal points, while outlier, which is white, are anomalies. The Koptok map represents anomaly score, with higher score indicating potential outliers. Isolation forest detects anomaly by isolating them faster than normal points, making it useful in foul detection and cybersecurity. This visualization shows the local outlier factors, methods for anomalies detection. Blue points are normal observation, while red points indicate outliers. RF detects anomalies by comparing local distances, making it useful for foul detection, security, and foul diagnosis. So for regression, this graph is a linear regression model, where blue points represent training data and red points indicate test data. The black line is regression line, modeling the relationship between variables. Linear regression is a key technique for predicting trends based on past data. This group shows SVM regression with blue training points, red test point, and a green regression line. SVM find a best fit line with a margin to minimize errors. The model generalizes well, handling linear relationship while being robust to noise. This graph shows how right regression condition changed with alpha. So alpha value result in minimum regularization, keep well constants. As alpha increase, the wave shrink, preventing overfitting and improving generalization. The last graph is showing lossless regression, where blue dot represent actual data and the orange line is the fitting models. Losso use L1 regularization to shrink some confusion to zero, ending in feature selection and preventing overfitting. So this is my part. Now I'll pass to Pisan for the conclusion. Thank you.
For classification model, which are random forest, decision tree, and KNN, we achieve high accuracy with 0.996242, but struggle with minority class detection due to class imbalance, making accuracy misleading. In anomaly detection, isolation forest detects global anomalies, while local outlier factor identify localized deviations. The best method depends on the type of anomaly. For clustering models, which are K-means, DPS-CAN, and GNM, we found weak agreement with actual labels as shown by a low adjusted RAND index. Lastly, regression models, which is linear, lasso, and ridge regression, show minimal differences. Lasso helps with feature selections, while ridge prevents overfitting. Overall, the choice of model depends on the data characteristics. While our models perform well, there were key limitations. First, class imbalance in classification skew model performance, making it harder to detect minority classes. Second, the lack of ground truth labels for clustering made validation challenging. Finally, algorithm selection bias may have influenced the result, impacting model failures. Addressing this issue would improve model reliability. To improve model performance, we suggest the following, which is: first, address class imbalance using techniques like SMOD, undersampling, or cost-sensitive learning. Second, enhance clustering validation by obtaining ground truth labels or using alternative metrics. Finally, explore advanced algorithms such as deep learning, hierarchical clustering, or ensemble methods for better accuracy and insight. That's all from us. Thank you.